James Webb Space Telescope is revealing the universe like never before.
And what you can see is actually material falling into a black hole.
The James Webb Space Telescope has been key to revolutionizing our understanding of the cosmos. It's given us the ability to peer into the depths of the universe. While doing that, it's found something absolutely unbelievable: 770 galaxies inside a black hole.
This is an image of Stephan's quintet, 5 galaxies that are interacting with each other.
Join us as we dig deeper into this discovery and how it affects us and the universe as we know it.
What you're seeing here is the telltale signature, the chemical fingerprint of water vapor in these atmospheres.
JWST is equipped with a suite of cutting-edge scientific instruments, meticulously designed to observe the universe across an unprecedented range of wavelengths. With a primary mirror spanning over 6.5 meters in diameter, the telescope dwarfs its predecessor, the Hubble Space Telescope. This colossal mirror allows JWST to collect and focus light from distant celestial objects with unparalleled precision and sensitivity. The telescope's instrument suite includes a powerful near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and a fine guidance sensor, near-infrared imager, and slitless spectrograph. These instruments work together to capture images, measure spectra, and study the properties of objects ranging from the earliest galaxies to planets within our own solar system. One of the things it's great at studying are black holes. Black holes are cosmic entities that result from the gravitational collapse of massive stars. When a star exhausts its nuclear fuel, it undergoes a cataclysmic event known as a supernova. During this process, the outer layers of the star are expelled into space, leaving behind a dense core. If this core's mass surpasses a critical threshold, approximately 3 times that of our Sun, gravitational forces become so intense here that they cause the core to collapse further, forming a singularity at its center. This singularity is a point of infinite density and gravity, hidden from direct observation. But the James Webb Telescope is able to look further than any other piece of technology has ever done before. One of the craziest things it's detected is the presence of 770 galaxies inside a black hole. This shouldn't be possible because it challenges the way black holes work. One of the defining features of a black hole is its event horizon, an invisible boundary beyond which escape becomes impossible, even for light itself. This boundary marks the point at which the gravitational pull of the black hole becomes so intense that not even photons, the fastest entities in the universe, can get through it. Any object or radiation that crosses this threshold is inexorably drawn toward the singularity at the heart of the black hole, a fate from which there is no return. That's not even the craziest part of the whole thing. The extreme gravitational pull near a black hole leads to a phenomenon called time dilation. What happens here is that as objects approach the event horizon, time appears to slow down relative to observers located farther from the black hole. This effect, predicted by Einstein's theory of general relativity, results from the insane warping of spacetime caused by the immense mass of the black hole. The event horizon isn't exactly a tangible surface like the hard shell of a celestial body. Instead, it represents a mathematical line beyond which the very fabric of spacetime behaves in a way that defies our intuitive understanding of the universe. The presence of a black hole's event horizon is what makes them so difficult to study directly, but that doesn't mean it's totally impossible. Their influence on the surrounding space, such as the gravitational lensing effect, a distortion of light due to the immense gravity, provides indirect but crucial clues about their existence and characteristics. One of which is gravitational lensing. Gravitational lensing is a phenomenon predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects like black holes bend the fabric of spacetime around them. When light from a distant object passes near a massive body, the path of the light is bent, resulting in a visual distortion or magnification of the object's image. Massive bodies, like stars or black holes, are particularly effective at causing significant gravitational lensing due to their immense gravitational pull. Among these, black holes represent one of the most extreme examples, with their incredible mass and compact size leading to pronounced lensing effects. As light from a background object like a star or galaxy approaches a black hole, it follows a curved path in the curved spacetime around the black hole. This causes the light to deviate from its original trajectory. If the alignment is just right, the deflected light rays can converge to a focal point, creating a recognizable image of the background object. This effect is similar to how a magnifying glass focuses light to form an image. Depending on the precise geometry, gravitational lensing can produce multiple images of the same background object. In some cases, a complete circular ring of light, known as an Einstein ring, can form around the black hole. This occurs when the source, lens, which is the black hole, and observer are perfectly aligned. Gravitational lensing can be categorized into strong lensing and weak lensing. Strong lensing results in clearly visible and distinct multiple images, while weak lensing produces subtle distortions in the shapes of background objects. Gravitational lensing has become a powerful tool in astrophysics. It allows astronomers to study distant and faint objects that would otherwise be too dim to observe directly. By analyzing the lensing patterns, scientists can infer crucial information about the mass, shape, and distribution of matter in the vicinity of the black hole. With advancements in technology and the launch of sophisticated space telescopes, such as the James Webb Space Telescope, scientists anticipate even more detailed and precise studies of gravitational lensing effects around black holes and other massive celestial bodies. With all of that, it's also possible that there's a lot going on inside black holes that you wouldn't even expect. But it's also possible that there's something else going on here. What if what we think is a black hole is actually a wormhole instead? Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures that emerge from the equations of general relativity. They are seen as tunnels or shortcuts through space-time, potentially connecting two separate points in the universe, or even different universes entirely. Essentially, a wormhole would be a sort of cosmic tunnel that offers a shortcut for travel across vast cosmic distances. One of the most intriguing and speculative ideas is that extreme conditions near a black hole's singularity could end up giving rise to a traversable wormhole. This concept arises from the notion that the extreme warping of space-time near a black hole might create conditions conducive to the formation and stability of a wormhole. The formation and stability of a traversable wormhole within a black hole would likely necessitate the existence of exotic matter with a negative energy density. This hypothetical form of matter, not observed in our universe, would possess properties that are totally different from conventional forms of matter. Wormholes also raise fascinating questions about time travel. If a traversable wormhole were created and found, it might offer a means to potentially bridge not only vast cosmic distances, but also different points in time. While it's possible that's what's inside a wormhole, it's also possible that exotic matter is what lives in the darkness there. This is a form of matter that possesses properties unlike any known particles or energy forms in the observable universe. One of the intriguing aspects of exotic matter is its property of negative energy density. In conventional physics, energy density is expected to be positive, meaning it contributes to the overall positive mass energy content of a system. But exotic matter is said to have a negative energy density, a concept that challenges our everyday intuitions about energy. One of the most notable theoretical applications of exotic matter is its potential role in the stabilization and sustenance of wormholes. Wormholes would inherently be unstable and would tend to collapse or become impassable due to their extreme curvature of space-time. Exotic matter with its negative energy density, when carefully distributed around the wormhole, could counteract the gravitational forces trying to collapse it, allowing for a stable and traversable conduit through space-time. What's unique here is that exotic matter is composed of exotic particles or fields that differ significantly from the particles found in the standard model of particle physics. These particles have unique properties, such as negative energy density, which make them distinct from ordinary matter. It could interact with known particles and forces in unconventional ways. It might have repulsive gravitational interactions, as opposed to the attractive gravitational force of ordinary matter. These interactions could be mediated by hypothetical particles or fields not yet discovered or fully understood. But what if it's neither of those, but instead, white holes? White holes are theoretical objects that, if they exist, represent the reverse of black holes in terms of their behavior and effects on the surrounding space-time. While black holes are known for their intense gravitational pull, which prevents anything, including light, from escaping beyond their event horizon, white holes are hypothesized to be regions of space-time from which nothing can enter. Instead, they expel matter, energy, and potentially even light, essentially the opposite of black holes. The concept of white holes arises from mathematical solutions to Einstein's field equations in general relativity. These solutions suggest the existence of the regions of space-time where matter and energy emerge, analogous to how they are drawn into black holes. The key characteristic of a white hole is that it allows only the outward flow of matter and energy. Nothing can cross the event horizon from outside to inside, making it fundamentally distinct from black holes. Some theoretical discussions of white holes raise intriguing questions about their temporal properties. For example, it has been speculated that the flow of time within a white hole might be reversed, leading to scenarios that challenge our normal understanding of causality. One of the most fascinating aspects of white holes is the potential connection they might have with black holes. Some scientists have proposed the idea of a wormhole bridge, linking a black hole and a white hole, suggesting that they could be different aspects of a unified phenomenon. In such a scenario, matter falling into a black hole might emerge from a white hole in a different region of space-time, or even a different universe. It's possible that the 770 galaxies ended up there because of a white hole and are just being seen. Or maybe there have been multiple galaxies all around us this whole time. The concept of the multiverse posits the existence of multiple universes, each with its own set of physical laws, constants, and conditions. These universes may coexist alongside our own, potentially offering a vast array of diverse and distinct realities. Within the framework of the multiverse hypothesis, black holes have been speculated to serve as cosmic gateways or connections between different regions of the multiverse, or, other galaxies. This idea is based on the extraordinary gravitational forces exerted by black holes, which can bend and warp space-time to an extreme degree. Black holes could represent passages or bridges that allow objects, particles, or even information to traverse between different universes within the multiverse. Each universe within the multiverse could possess its own unique set of physical laws, constants, and properties. Transitioning through a black hole might enable an entity to experience and interact with these varied and exotic physical realities. So what really is in a black hole? Physicist Stephen Hawking talked about the black hole paradox in the 1970s, and it might bring us closer to the truth here too. Hawking's groundbreaking research on black holes led to the discovery of what's now known as Hawking radiation. This radiation is a form of thermal radiation that black holes are predicted to emit due to quantum effects near the event horizon. The paradox revolves around the fate of information that falls into a black hole. According to classical physics and general relativity, when matter crosses the event horizon of a black hole, it is believed to be irretrievably lost. This is because the intense gravitational pull of the black hole prevents any information from escaping, even in the form of light. But the emergence of Hawking radiation introduced a quantum mechanical aspect to the behavior of black holes. This means that the particles can spontaneously appear and annihilate in a vacuum. Near the event horizon of a black hole, this process leads to the emission of radiation. This raised a fundamental question. If black holes emit Hawking radiation, it suggests they can lose mass and eventually evaporate completely. This process seems to imply that information that was once inside the black hole is being radiated away. This challenges the classical notion that information is permanently lost in a black hole. The black hole information paradox has profound implications for our understanding of the fundamental principles of physics, particularly the interplay between quantum mechanics and general relativity. It has sparked intense debates and prompted a wide range of proposed resolutions. Resolving the black hole information paradox is challenging because it requires a deeper understanding of the quantum nature of gravity, which remains an area of active research. But that's not the only thing. There's also black hole firewalls. Firewalls are proposed by some physicists to address the apparent conflicts between general relativity and quantum mechanics near the event horizon of a black hole. They represent intense regions of radiation that are postulated to exist very close to the event horizon, potentially replacing the conventional concept of a smooth and benign horizon. This would bring together two fundamental principles of physics: general relativity and quantum mechanics. At the heart of the issue lies the question of what happens to information that falls into a black hole. Quantum mechanics suggests that information should be conserved, while general relativity implies that it might be lost behind the event horizon. Firewalls attempt to resolve the black hole information paradox by positing that information is not lost within a black hole. Instead, it would be encoded in the intense radiation of a firewall, which would be encountered by any object or particle crossing the event horizon. Introducing firewalls challenges the smooth and predictable nature of the event horizon, as described by general relativity. Instead of a gradual transition, firewalls propose an abrupt and highly energetic boundary layer, fundamentally altering our understanding of space-time near a black hole. Firewalls are a manifestation of extreme quantum effects near a black hole. They imply that the energy density and curvature of space-time near the event horizon are much higher than previously thought, leading to conditions that defy our classical understanding of gravity. They're similar to fuzzballs. They challenge the traditional notion of black holes having singularities at their centers and go the completely other way. Black holes may be structured as dense, stringy configurations of quantum states, but in this model, the singularity is replaced by a complex and intricate network of quantum phenomena. In the fuzzball model, the interior of a black hole is envisioned as a tangled web of extremely compact and highly entangled strings and other quantum entities. These strings are fundamental objects in string theory, a theoretical framework that seeks to reconcile quantum mechanics and general relativity. One of the primary motivations for the fuzzball hypothesis is to address the black hole information paradox. By replacing the singularity with a stringy structure, the hypothesis aims to provide a mechanism for preserving information within the black hole, potentially avoiding the information loss problem. The idea of fuzzballs seeks to avoid the need for a hypothetical firewall near the event horizon, which is proposed in some other theoretical approaches to black holes. By redefining the interior of a black hole, the fuzzball hypothesis offers an alternative to the conventional notion of a singularity. The fuzzball hypothesis aligns with the principles of quantum mechanics and string theory, which emphasize the discrete, quantized nature of physical phenomena at the smallest scales. It attempts to provide a more consistent description of matter and energy within the extreme environment of a black hole. But all of this brings us back to galaxies being inside black holes. All of the theories that we've talked about until this point seem to follow one pattern. They all exist on their own, with no space for anything inside them. Galaxies could exist around them, but not inside. The idea challenges our fundamental perception of reality. If galaxies can exist within a black hole, it suggests that our understanding of the universe may be limited or incomplete. This raises questions about the true nature of the cosmos and what lies beyond our current comprehension. It highlights the inherent limitations of human knowledge and the scientific method. Our understanding of the universe is based on observations and theories developed within the framework of known physical laws. The concept brings up epistemological questions about how we acquire knowledge. It forces us to consider the validity of our current scientific paradigms and whether there may be phenomena beyond our current observational capabilities. If this concept is now becoming a reality, it already raises ethical questions about the exploration and study of such environments. How would we approach the investigation of galaxies within a black hole? What are the ethical considerations surrounding potential future technologies that could probe regions like this? We might actually have to reconsider the nature of space-time and whether it may be more complex or interconnected than we currently think it is. This has implications for philosophical debates about the nature of reality and the fabric of the universe. Maybe things haven't been the way they seemed, and it's us who've been in the dark this whole time. If black holes can contain entire galaxies, it means they're a lot more important than we thought, and it might be time to shift our focus from other planets to black holes. Who knows what else we might find? What do you think about the potential of galaxies inside black holes? Let us know in the comments below.